the temperature was less, where the temperature was less than where the temperature was less than 17 degrees. So it's our winter conditions. This is the most conservative assessment. It's a nature-based solution, so the temperature, the irradiance will not be optimum for algal growth, oxygen production, etc. So it's to ensure that the system will work in winter, not only in summer conditions. And the validation had to be operated over 10 weeks. And that involved collecting 2 inlet and 2 outlet samples per week on different days, because you have to account for different any flow variation that may take place over the week. And we were looking at E. coli and this phage of E. coli that's present in fecal material as the viral indicator. And we had to then calculate the log reduction value, the difference between inlet and outlet. But even more stringent requirement was the values were not taken as means or medians. The value that was accepted for the validation was the 5th percentile. And if you think about that, if we take 20 samples, 20 inlet, 20 outlet samples over 10 weeks, the log reduction value you get is for the poorest performing sample in your data set. It's accepting the worst case value, not the mean or the median. And we did this in 2013. So that was the setup: septic tank, wastewater into 2 high rate ponds. Combined retention time was 10 days. Measured the LRV, and that was the sort of temperature. The mean daily air temperature was 25. It was quite a warm winter at that time. Solar exposure. Solar exposure was pretty typical for that period of time. And the inlet values from the septic tank were quite high: 250 milligrams, 61 milligrams of suspended solids, and a fairly turbid wastewater. But the key part was we were required to meet particularly a log reduction value for the virus surrogate. So in public health terms, the departments of health are really more concerned about viral disinfection, because there's a view that if you have one infectious viral particle and a susceptible person, a person susceptible to that virus particle, then they're likely to develop the infection associated with the virus. So they're really interested in viral removal rather than E. coli removal. And what this slide's really showing is here, when we looked at the whole system in series, we were required to have a 1 log removal, so a 10-fold removal of virus inlet to outlet. And we met that requirement for the 5th percentile. It was actually 1.6. So this work was published in 2018. And essentially the system, the high rate algal pond, satisfied the independent validation as an acceptable treatment system. So it was validated. It was performing better than the minimum requirement. It was validated as a system. So now the pond systems that we use in South Australia, they're validated for. Currently, Kingston-on-Murray operates as 2 high rate ponds in parallel. Each pond receives about 6,000 litres of water, operates at a 10-day residence time, and it goes to irrigate eucalyptus plants, eucalyptus trees, as the final disposal pathway. So this was quite significant in the sense that it was the first time, as far as I was aware, still is as far as I'm aware, the first time a high rate pond had actually been independently validated to national guidelines, and then we high rate algal ponds for use in South Australia. So what this meant was that any consultant engineer, any community who wanted to upgrade their wastewater treatment could adopt high rate algal ponds and include them in their treatment system. And that was the first time globally that any design guideline had been published like that. So it means now that engineers, that the guideline has some design drawings, some operational parameters, and they could include a high rate pond in the treatment train, and they've got no requirement to come to me. I've kept no intellectual property. I've got no financial interest in it. It's now just public good research where any engineer could use these and use these guidelines and install a high rate pond. The guideline accepted two configurations. I don't want to go into too much detail, but the treatment train that's been agreed is, in the absence of a septic tank, there'd be anaerobic ponds prior to the high rate pond. So if you remember, anaerobic ponds were included in the waste stabilization pond design as the first ponds, 4-meter deep, 4-day residence time, organic carbon removed via anaerobic bacteria, suspended solids settle in the ponds, and then the liquid phase goes on into a high rate pond operating at 10 days. There are other organisms that can be a risk. Helminths, where they are endemic. We don't have endemic. These are worms basically that infect people. Associated with cattle, we don't have them as endemic in South Australia, but they were included in the guidelines in case the guidelines were used elsewhere that did have these organisms endemic. And the total residence time now is 25 days, 10 days in the high rate ponds and 15 days in a storage pond. So this was quite a significant achievement, really, to get high rate ponds on the accepted as treatment systems. And it was recognised, our publications, we were invited to go to the Bill and Melinda Gates Foundation to attend a case study meeting where they were looking for risk-based adoption of new treatment systems that used a risk-based approach to validation and acceptance. And this was part of, to support the World Health Organization's Sanitation Safety Planning Manual. And our case study for Kingston-on-Murray was included in that as a means of demonstrating how you would validate a new treatment system for adoption for use in any country, really. Wasn't saying that high rate algal ponds could be used in any country. It was accepting that the method of validation was quite rigorous in Australia, and the WHO at the time were just starting to adopt a risk-based management approach to new wastewater treatment trains, and this was adopted for that. Subsequently, so we now have guidelines in South Australia. Kingston-on-Murray that we were talking about was down here. Subsequently, we were asked if we would design a high rate pond for Peterborough. And Peterborough is about 280 kilometres away from Adelaide. So I'm talking to you down here in Adelaide. And Peterborough is a township in what we call the mid-north. After that, this is all outback and desert country. After that, it really changes at Peterborough and becomes really quite challenged for water availability in summer. Currently today, we've had a day of about 37 degrees today. And out here around Peterborough, it's probably up around 40. So it's quite challenging environment. And Peterborough is a township of about 1,700 people, but it also has an abattoir out here. And interestingly, the abattoir is in Australia, we have camels, and the camels were used to transport goods in the 1800s. And when the event of trains and better transport, the camels were turned loose. And now there are millions of camels in Australia. And this abattoir uses Aboriginal members of the community to muster these camels to get them together and put them on trucks, and they bring them down to the abattoir where they're slaughtered and butchered, and the meat is exported into the Middle East. But because it's an export abattoir, it uses quite a lot of water for washdown and cleaning in the process area. And the high rate pond also treats not only wastewater from the community, but also from the abattoir out here. And the ponds have been built here. The high rate ponds have been built here. So Peterborough, that figure's changed now. It's about 30% of properties connected. So Peterborough has about over 1,000 houses, nearly 4,000 people, has the effluent. Because of the abattoir, the flow rate into Peterborough was, before COVID, before the pandemic, was estimated at 470,000 litres a day, which was quite a large high-rate algal pond. And it was constructed in 2019, just before COVID, and it comprises of 2 anaerobic ponds here and 2 high-rate ponds. This one is empty because we haven't got 100% of the connection to all the properties. So this one's the functioning high-rate pond currently, and then these are water storages. So the treated effluent will go into this storage basin. This is now full of treated water, and this water then goes to irrigate a golf course, sports ovals. So it's beneficially used. And Peterborough is quite a step up. So Kingston-on-Murray was 250 square metres, and the validation was conducted at Kingston-on-Murray, and Peterborough is 5,000 square metres. So the combined area here, this is a hectare of high-rate algal ponds out at Peterborough. It's quite novel in that whereas Kingston-on-Murray only had 2 channels, Peterborough has 6 channels as a meandering channel design. The wastewater meanders through. This is a paddle wheel mixing system. The combined length of the channels, subsequently, this was our original estimate, but subsequently it's been shown to be over 1 kilometre long. The total length of the channels are over 1 kilometre. The channel width is about 3.4 metres. It's got the retention time for the guideline value of 10, and it's got a lot of irrigation storage prior to being distributed for crop growth. Move on. So this was the early days, and this is when the plant was the ground was being prepared, and this was the start of a relationship we've had, a collaborative relationship with Jeremy, his daughter, and Jacques Legrand, who's also with you guys in Saint-Nazaire. And this has developed into a really productive collaboration with JPA and the colleagues at Nantes, which I'm going to say a bit more about in this lecture and what we've achieved. And you can see how the ponds were constructed. So these are earthen banks. The channels are cut into the earth to make the shape, and then the channels are lined with the same material here, a butyl liner. All our in-ground ponds have to be lined so we don't contaminate groundwater. Makes it quite expensive to do, and quite time-consuming to make the liner shape around the bends. And then this is it now as it currently looks in terms of size. So these channels are 170 meters long, each channel, and they're mixed by a single paddle wheel in this meandering channel design, and you can see it's really quite green at the time of this this drone footage. More So that's the paddle wheel doing the mixing. It's interesting that people ask what these tires are for, why they're there, and it's when you're building the pond, they're used to keep the liner because there's no water in the channels. If you get high winds, they can rip the liner apart. So a cheap weight is just to go to a tire um, disposal yard, and contractors get a lot of tires and put them in the channels the to weight the liner down so it doesn't fly off in high winds. And we do get high winds out in this environment. And somewhat we were very pleased to win the South Australian, our own state awards for infrastructure project innovation award for the council, Peterborough Council, Flinders University, and the Local Government Association. So that was nice to see that the work we'd gone from research to validation to translation and adoption, and it was valued by the wider community. So we feel as though we've got high rate ponds on the agenda as effective wastewater treatment systems, which is a plus, I think. So I'm going to change to another lecture. Have you got any comments on that? Any discussion you'd like to have?
Well, it was kind of impressive. It's a really large canals of water there.
Yeah, it's quite an interesting system, and I think one of I made the comments I think in a previous lecture that we're still having we see it in some publications where people are still commenting, other researchers commenting on the potential for algae to do wastewater treatment,
Hmm.
and talking about single strains of algae, etc., etc. And I think I noted in the previous lecture the meeting we were at in Portugal this year. Both myself and Spanish group we agreed that these systems have matured and they are suitable for wastewater treatment in obviously in certain conditions, certain climates, temperate Mediterranean climates, etc. And they are, I think, Kingston Murray and Peterborough in South Australia demonstrates that they can meet national guidelines for wastewater treatment on, for specific and fit for purpose end use of the wastewater, and that's irrigation of non-food crops. Uh, and it's, I think, an important step forward for regional and remote communities. So I think they've come of age, is what I would say. They've actually matured, and they're a technology that could be adopted. And the question is, how do we persuade engineers um, who are used to pouring large concrete structures and intensive aeration systems using lots of energy? How do we get them to start thinking about nature-based systems for wastewater treatment? I think competing technology would be wetlands. They seem more comfortable with adoption of wetlands for wastewater treatment, but there's certainly these algal systems. They offer smaller area requirements, greater efficiency, and an effluent that meets discharge guidelines.
Hmm. And
Any other?
the water that it's being treatment, I mean, yes, there is being treatment in here. It's also being distributed to population.
Yeah, it doesn't get distributed as any sort of drinking water. What happens is it goes out after storage in these basins here.
Hmm.
It goes out. There's a pump station here, and the water from this gets pumped to a golf course, which is up over in this part of the country, a golf course, and it goes back into town to irrigate a sports oval and trees and green spaces. So
Okay.
it's used. It replaces drinking water being used for irrigation. So the golf course previously used, really expensive, high quality drinking water, and now it no longer uses that. It uses the treated wastewater from the high rate pond and saves a lot of money and saves a lot of high quality drinking water from being used to irrigate grass.
Okay. And what are the new problems to solve with this system? Is there more investigations to do to make it even more efficiently,
Yep.
or
Yep, I'm going to talk about that in the next lecture and try and
okay.
encourage you guys to think about how you might get engaged in research like this.
All right. Thanks.
Okay, so I'll stop sharing this one and share uh, this one. Okay, are we ready? So I'm going to talk a bit about um, our collaborative relationship and what we've achieved working with colleagues Pierre, Jeremy, Mariana, Guillaume. We've had a really successful collaboration. Just really, a PhD student completed this year, and I'm just going to introduce this because we think this collaboration is really very valuable, and we'd like to continue it in this space in terms of wastewater treatment using algae. And we'd be interested to talk to students who'd like to join us in the adventure, because it is an adventure. So I'm just going to talk a bit about research, what we've done, initially building on Peterborough. So this is a paper we published this year in 2024, and I don't know whether you have met or are aware, but Selene Johan, we have the opportunity, both universities of Nantes and Flinders have the opportunities to sort of share a student. So a student can, Selene spent enrolled in University in Nantes, spent 2 years working in Saint-Nazaire, and then in the third year of her PhD, she came to Flinders, and she worked on Peterborough for a year with me and my students. And then when she writes her results up on her PhD thesis, and she's successful as she was only about a month ago, she finished. She was awarded her degree. She's awarded a degree from both universities. So she gets her degree from both University of Nantes and Flinders University in Australia, which is rather nice. And she got time to work with laboratory cultures, laboratory systems, to try and better understand, when you asked about research, to try and better understand how the algae and bacteria were actually associating, and where was carbon going, how was carbon used by the system, by the bacteria, by the algae, to try and understand better the growth conditions, and whether the algae were only growing through photosynthesis, autotrophy, whether they were growing as heterotrophic organisms, or whether there was a combination of using both organic substrates and carbon dioxide. And better understanding that is a challenge, and it could lead to some interesting operating strategies. But what Selene did, we were interested in characterizing this large high-rate algal pond. And as I said, it's over a kilometre long, it's 3.4 metres wide. And we wanted to understand, there was a lot of questions when we've talked about it and presented it in various various conferences. And even when we were designing it, some of the engineers felt that could we rely on one paddle wheel? to mix such a length of channel. So one of the first questions we wanted to answer was, how well mixed is this long raceway? Is it homogeneously mixed, so that there's homogeneous conditions, which is one of the big advantages of the high rate pond, is you don't get thermal stratification, you don't get differential microbiology between aerobic and anaerobic conditions, you don't get big temperature differences. So we wanted to look at how well mixed is this system with one paddle wheel. Paddle wheel's only rotating at 12 revolutions per minute, so it's not, you saw it, it's not spinning really fast. How does it mix? So paddle wheel here, this is from this paper that Selene's excellent diagrams that she included in her thesis on this paper. So the paddle wheel's here, the wastewater comes in here from the anaerobic ponds, and what we did was we set up these sampling stations along the flow path, so the wastewater flows in this direction through the channels and then back round. The travel time for a wastewater from here back to here is just over 3 minutes. So it takes about 3 minutes to do the traverse of the kilometre. And what we wanted to do was, excuse me, we wanted to look at conditions within the pond at these points to see how they might change along the channel length. Is that okay? Any questions?
How much it was to go to all the channels? 3 minutes? For the paddle?
Sorry, I didn't catch that.
The 3 minutes were that you mentioned was for what? Sorry,
It's for if you put a particle. I mean, one of the fun things to do with these systems is just to put an orange in, just the fruit. You put a fruit in. I mean, if you want, a nice visual, it's got a low. It's neutrally buoyant, so it sits really low in the water. It's easily visible. Using that as an example, it would take your orange from here, put in the water here to do the length to here. The transit time is about, if I remember correctly, a transit time is about 3 minutes 40 seconds for the orange to go from here through the pond back to here. Yeah.
Okay, so the panel gets in that same position all the time and just is the
Yeah.
water.
Oh, yeah. The paddle wheel is a significant piece of infrastructure. So it's in this mounting here all the time. The paddle wheel's fixed, so it's pushing water. It's basically acting as a pump. It's changing the head. It's lifting water from this side down to here, and basically pushing or pumping it round is the way the paddle wheel works. So we're talking about putting a particle. My example is an orange, and timing how long the orange takes to go from here all the way around back to here, and it's about just over 3 minutes, basically.
Okay. Yeah.
Which I think is quite reasonably fast, for this paddle wheel
Yes.
to be pushing along a kilometre. It's doing a lot of work in that time. So what we did was at each station we took samples and we took measurements. So we'd take a measurement at cross section 1, take the measurements, move to cross section 2, take the measurements, move to cross section 3. This took a considerable amount of time and a lot of students involved. These are Felipe's one of my students, Sam's one of my students, and these are the people who designed the experiment and were supervisors. So 3 days out in the field doing these measurements over a 3-day period. And the way we did the sampling was we built this gantry. So this is the cross section of the pond. This is a metal rods. These are metal rods going down into the pond. This is the water level, 300 millimeters, and attached to these graduated bars, we could put water sensors. We could put oxygen probes, pH probes, temperature probes, and velocity probes. And we could take measurements by changing the elevation of this gantry. We could take an oxygen measurement at the bottom of the pond. We could then raise the gantry, take a measurement at the mid depth in the pond, and take a measurement just below the surface. So we could get a profile of oxygen, temperature, pH through the pond depth. And we could do this at all these 3 points in the left-hand side of the channel, center, and right-hand side. We could basically we would end up with 9 data points, three from each horizontal position across the pond. So we had 9 data points throughout the pond depth. And we also, at the same time, we had tubes attached to these rods as well, and we had a pump. So at the same time as we were measuring dissolved oxygen temperature, pH, flow velocity, we could take a sample at bottom, raise the bar middle, raise the bar top, and we could take samples at all 9 sampling points. So it was quite a considerable effort. Are you okay with that? Any questions? All clear? Okay. So the first thing that we did, we were saying this is a 3D characterization. So when you're looking at doing flow measurements in these systems, you take, in this case, you take the left bank as when you're looking down the direction of flow. So here, the left bank is this bank. Here, the left bank is this bank on this side of the pond. Okay, so you have to orientate yourself as being the left bank looking in the direction of flow. So what we've got here, these panels, these squares, these are this is the right bank, center, left bank, and then this is the depth, top, middle, bottom. And we did that at all cross sections. Okay, all the way through, 26 measurements. And then these are the return bends. So the bend that gets you back, this bend, the one that gets you back up here, this bend is the one that brings you back to the paddle wheel. And what we've got here is these are the flow velocities measured in meters per second. So here, when you've got a dark blue, you have virtually no flow. Whereas here, you've got a flow of 0.5 meters per second, the liquid flow velocity. And what you see is it's really quite homogeneous. You know, you're talking about 0.3 to about 0.5, some lower ones. But what you really see, what really stands out, is that when you come round, so the liquid is flowing, it comes round the bend to go down this channel, the flow velocity drops on the left bank because this is where your channel divider is. So what we're saying is you come round, liquid flows very rapidly on the outer surface of the bend. On the inner surface, it starts to slow down. And in actual fact, you can get reverse flow where the liquid flows circulates in eddies, in vortices, and flows back up the pond because of the nature of the flow velocity here. But overall, we think this is really quite a well-mixed pond with the single paddle wheel. And the mean flow velocity in here was 0.2 meters per second in the whole channel. I don't know. I think, is Pierre still in the room? Does Pierre, do you want to add anything to that?
I think you sum up pretty well. I think we can add is how the CFD involved behind it and how the
Yep.
models were used to do that. And we need like supercomputers to run
Yep.
such big model. And that's what is pretty innovative because there's been work on raceway modelization for hydrodynamics before, but for HRAP and HRAP of this size, that's on an innovative part. And as you mentioned, maybe a bit, maybe this next slide is a comparison between what model gives
Yep.
and what was actually measured on field.
Yep.
Yeah.
So what we've got here on the right hand side, there's one of the students on this paper also was doing her master's degree with me at Flinders University, and she was interested in computational fluid dynamic modelling. And with colleagues at another university in Melbourne, Royal Melbourne Institute of Technology, they had access to really powerful supercomputers used for modeling aerodynamics for flight and for various aeroplanes. And what we did, or what was done, was to do a CFD model in the same sort of dimensions. And what you can see in the model is really what we measured here. So you get areas here where there's low flow velocity. With the liquid, this is the paddle wheel here in this diagram. The water's flowing in this direction, comes round the bend, and you get these. I'm not going to show you any more images of this, but you get this area of really low flow velocity down the inner side of the channel divider. And in some cases, you'll get negative flow velocity in the sense that the velocity is actually going against the direction of flow of the bulk fluid. And this is one of the, we're not aware of any other study that's done a CFD model to such detail as this one that was done by Regina. And that's an area we would really like to do a bit more on with Pierre, is to have a look at a bit more validation of CFD, maybe have a look at how we might improve if we need to mixing. Certainly we could improve by inclusion of baffles, but it's a really interesting area, and being able to have access to a very large pond system, to be able to model a very large pond system, is really unique. There's no other. This is the only high rate pond of its nature in Australia, and it's also one of the few worldwide that actually have multiple channels. In Peterborough, we had to have multiple channels because the area that was available to put the treatment system in was relatively small. So we took the view that we should do this, and certainly in terms of flow velocity, we've been vindicated that the pond is really well mixed with this single paddle wheel, and we've got some really nice CFD modelling. And I should say what Pierre's noting is, I think it's relatively rare. You can often see CFD models. I mean, there's one by a guy called Kurt Liffman who did one in the early 2000s, but it's only of a single channel, a single raceway with two channels, not a multiple one like this. And it was generally, these models, they're found very difficult to validate. Whereas here in Regina's thesis, we have the CFD model, and we have the in situ velocity measurements that were measured across 9 points in the pond at 26 locations in the pond. And that's some work we're looking to, we're working on publication with Pierre and Regina, where we've got a large high rate pond that the velocity's been measured and the pond's been modelled, and there is very good agreement between the actual measurements and the CFD model, which we're pretty excited about. Is that a fair comment, Pierre?
Yeah, absolutely. And actually,
Yep.
Howard, if you have a minute during the break, we should talk about the purification
Yes. Yeah, that
because
would be good.
there is many things I want to tell you on this. So yeah,
Right. Excellent. Okay, let's do that. So that was the first part of this study, and of course that's only one measurement we had on the gantry was flow velocity. The next one was we could look then, because we were measuring dissolved oxygen, we could look at dissolved oxygen as the water moved through the pond. So one of the questions when you do this was what could you consider, would you like to comment on methodology in this? What would be some of the confounding factors you think? You've got a large outdoor pond. You've got 26 sites you're trying to measure, and you're trying to determine whether there's differences in location. And if I remember correctly, we started at about 8 o'clock in the morning, and we didn't finish till about 7 o'clock at night. So it was a whole day. What's going to be a confounding factor in us trying to determine if there's any difference between this point here and this point down here over a period of 12 hours? What's going to be a factor that's going to be difficult that you have to control? Where's the major source of dissolved oxygen? Come on, don't be shy.
I'm sorry, what can you please repeat? Sorry, my internet
We've got
connection is getting badly, so can you please repeat?
Okay, so we've got a large outdoor pond. We're measuring dissolved oxygen, and we're trying to determine whether there is over a day, takes us over a day to do the measurements. We want to compare or determine whether there is a difference in dissolved oxygen here, just after the paddle wheel, as opposed to here, just before it returns to the paddle wheel. But it might take us, the difference between doing a measurement here and doing a measurement here might be 12 hours. What is going to be a confounding factor in that measurement? And think about what's the major source of dissolved oxygen in an outdoor high rate algal pond? Where is the dissolved oxygen coming from predominantly?
From microalgae, as per
Right.
sure.
So
Because they do photosynthesis.
yeah, okay. So what happens over the day to photosynthesis in an open pond? If we
Well,
start,
it's tough if it's not sun there. Well, not stopping, but need the sun.
yeah, it needs the sun.
Photosynthesis.
So what happens over the day though? Is the dissolved oxygen constant over the day, or how does it change over the day from say 6 o'clock in the morning to 10 o'clock at night? How does the dissolved oxygen change over the day?
Well, I see in the image, it's like I don't know how to say.
I mean, what you're
Start with a
expecting.
low oxygen, with a low dissolved oxygen, then you start to get in like a lot, but then like it normalize and going to 10. You know what I'm seeing here?
Yeah, but
Your green.
what I'm getting at is we're taking 12 hours to do this measurement. And over the day, if you've got sunrise, irradiance increases in the morning to a peak in the afternoon, and then decreases, in our case, probably about 3 o'clock in the afternoon, decreases, the irradiance decreases, and it goes to dark at 10 o'clock at night or whatever. And over that period of time, dissolved oxygen is naturally changing because there's more light available for photosynthesis. So the dissolved oxygen might be, 7 o'clock in the morning, it might have been 7 milligrams a litre. And
Mhm.
then by 3 o'clock in the afternoon, it's 20 milligrams a litre. And then by 6 o'clock in the evening, it's back down to 7. So it's naturally changing over the day And yet we're trying to measure differences between, is there a difference here between here and here? And it takes us 12 hours to do the measurements. So what I'm getting at is somewhere you have to be able to try and compensate for that diurnal change in oxygen production. So the pond is naturally having an oxygen production that does that curve, a bell-shaped curve. So what we had to do was compensate for that. And what we did was we had a static oxygen electrode that didn't move. It was placed in this point here, round about here in the pond, so on the second channel. And we took measurements from that static point and then compensated for the change over the day to compensate for that when we were doing different time measurements during the day. We had to have a set point to enable us to take into account the diurnal variation. And what's interesting, why I'm talking about that is we note here what looked like an aberration. We thought, wow, this is really interesting, because down here, the water coming back to the paddle wheel after it's gone down the length of the channel it's very high in dissolved oxygen. It's 10 to 13 milligrams. It's oversaturated. It's probably 150% saturated in dissolved oxygen. And what we thought when it went through the paddle wheel was it being deoxygenated? Because all of a sudden the oxygen's dropped from here. This is a body of water that's coming from here, going through the paddle wheel and back down that channel. And what it looked like was that the oxygen was really high here, and maybe the paddle wheel with its rotation was deoxygenating the water. And subsequently, we went back a second time to do the measurements. And this was actually, we acknowledge it and we discuss it in the paper. This is actually an artifact. What happened was the compensation for the diurnal change couldn't, there was a difficulty in doing that, and this was not confirmed by a second measurement where we just measured the dissolved oxygen here and the dissolved oxygen at this point. It did not decrease after the paddle wheel. It was an aberration of that particular day, because it took us 12 hours walking up and down this kilometre to measure this difference between them, to take a measurement here and take a measurement here. There was about 12 hours difference, and we couldn't properly compensate for the diurnal change that naturally occurs in dissolved oxygen. And it's just, I'm really just talking about it because it's practical microbiology. How do you do measurements on these very large systems, and how can you try and control for changes? How can you at least measure changes? And we know that the reason we couldn't get the compensation really as good as we thought we could was because this fixed probe here had a lot of biofouling. So there was algae and other material got around the oxygen probe, and the oxygen probe was not reading correctly. We didn't recognize that soon enough, that the probe was not staying clear of contamination, and that depressed the oxygen values at the set point, and it caused this aberration here. And it's a measure of, it's very nice. I mean, Selene used the Taurus photobioreactors that are available in Saint Nazaire, immensely controllable. Everything can be measured. But when you come out to a large system like this out in the field, it's quite challenging but exciting to do. But just an observation. Any comments on that? Have I gone too far in the problems of working with high rate ponds outdoors? No?
Yes, the dissolved oxygen at the end of the day, well, if it's big amounts of dissolved oxygen, don't affect microalgae. What did you think about?
Well, I mean, you would say that from the point of things like photorespiration, you may have conditions where you've got a lot of dissolved oxygen, but you've got very high light intensities as well. So you might get photoinhibition under those conditions. But don't forget what we said from the high rate pond is that at these high concentrations of oxygen, the net change in oxygen is efflux out of the pond into the atmosphere. But it may well have a negative effect, but you can't control for it. Whereas when you go to photobioreactors, you still have that negative effect, but you've got a lot of control parameters that have to be put in place to control to vent that dissolved oxygen to stop inhibition of algae through things like photorespiration, etc.
Okay.
Yep. I don't know, Mariana, if you're still in the room, if you'd like to comment on that at all.
Mariana had class over.
Okay.
She had to leave.
It's just you, Pierre, is it? Okay.
Yeah, it was
You
me.
can you can comment too if you'd like.
No, no, I mean, you did all. And I have Thibaut with me discussing. So I will turn off my microphone not to bother you.
Okay. So then, this is just an example of what we could do with the liquid samples we take. If you remember, I said you could take we could pump samples at each of the 9 points at each of at least of the 26 cross sections. We could take them, we could store them on ice, take them back to the lab, and we could analyze for inorganic nitrogen. And I've put it in the order, if you like, of oxidation. So most of the wastewater coming from the anaerobic pond will be ammonia, NH4N. We always measure that, we always report our results as the atom of nitrogen in this particular inorganic nitrogen, because then it's very easy to do a sum. We can just add this up because we're only measuring the atoms of nitrogen, small point. So here, most of the material coming in, very high ammonia concentrations, not very high, but reasonable, not as high as I was expecting, but they're about 9 milligrams a liter in the pond. Ammonia, as I've noted before, at high pH, NH4 will be in equilibrium with NH3, the gas. So at high pH that you'd expect during algal photosynthesis, the ammonia will actually leave the pond. So some of the ammonia will leave the pond and not be included in algal biomass or bacterial biomass. And that may well be what's happening here with the relatively low ammonia in the pond. It's very high coming in. Ammonia will be taken up by algae, and it will also be going out into the atmosphere due to the high pH in the pond system. But of course, what we talked about in the wastewater composition lectures and what happens to ammonia is where you've got high oxygen concentrations, which we have in the high rate pond, we will also have naturally occurring nitrifying bacteria. And we consider two broad classes of bacteria: the ammonia oxidizing bacteria, which will oxidize the ammonia through to nitrite, and the nitrite oxidizing bacteria that oxidize the nitrite through to nitrate. So we're looking here at the natural progression of the nitrogen cycle from reduced ammonia to oxidized ammonia in the presence of high oxygen concentrations, or oxygen that's available. Carbon dioxide is available because most of these organisms are autotrophs, so they need carbon dioxide. They use carbon dioxide as their carbon source. So if you've got the combination of oxygen, carbon dioxide, suitable temperature, you'll get nitrification. And what we see here is, yep, we've got reasonable amounts of nitrite and nitrate in the system. So it's oxidizing. But what's also interesting is this question here. When we look at ammonia, nitrate, we start to see lower levels of nitrate in the final channel before it goes back to the paddle wheel. And one of the questions we have here is whether either the bacteria are somehow being challenged for one of the substrates. what could be happening is that during the travel through the system, they start to aggregate and they start to go into aggregates of algae and bacteria. And when you get aggregated material, you can have microclimates where on the outside in the pond, on the outside of this aggregated material, flocks, where the algae and the bacteria are stuck together, you may have areas on the outside that are very aerobic, and the organisms are using a lot of oxygen. They're growing under aerobic conditions. The bacteria are oxidizing organic carbon. They're taking in a lot of oxygen, and in the center of the aggregated material, oxygen may not be penetrating to the center, and it might be anaerobic, and you get anaerobic reactions and maybe the release of ammonia from the wastewater. And that's a research question. We don't understand why we've got high rates of nitrification through the pond generally, and in this last channel here, we're seeing lower rates of lower concentrations of nitrate in this point. We could have a reaction where the nitrate is being denitrified. That is, the O2s that in reducing environments that might be in the center of the aggregates. The reducing environment means that the nitrate is reduced to nitrogen gas and leaves the pond as nitrogen gas. And that's a research question: is what is happening with nitrate here and the nitrogen cycle in this part of the pond. So there's a few questions about nitrogen. But overall, when we looked at this at the pond, we were really pleased that the pond had the design flow velocity, which is 0.2 meters a second. So the design was good. It was Selene in her paper uses the word surprisingly, because there was a lot of thought that maybe it wasn't going to be a very homogeneous environment. It wasn't going to be it wasn't going to be well mixed. But in actual fact, we've demonstrated that it is an extremely well mixed homogeneous environment for photosynthetic and heterotrophic activity. Photosynthetically dissolved oxygen was really high. It was oversaturated. It was over 20 milligrams a litre midday. That's the rates I've shown you are the ones in the pond were the ones corrected so we could compare the 26 points. But during the day, it was up at 200% saturated in the diurnal cycle without us correcting for that cycle at each time of measurement. It looks like that nitrifiers may be impacted by lack of turbulence due to distance from the paddle wheel. That is, that they were aggregating. There was microclimates being formed because they were sticking together with other bacteria, polysaccharides, etc. And maybe there was insufficient oxygen available to them at specific locations. That's an interesting question. It would be good to look at local mixing velocities. It'd be good to be able to look at redox potential within the algal material. I said to you earlier that in these ponds, we don't see the algae growing as single cells. They're usually in a floccular biomass. They're usually stuck together. They're usually mixed with algae and bacteria, and that leads to microclimates. And it would be really interesting to try and understand those better about microclimates within these floccular materials. Now, I'm conscious that I was instructed to give you a break at this time with you. So I'm going to give you a 15-minute break. So my reckoning is it's 9:15 with you in the morning, and we'll come back in 15 minutes. Is that okay? Firstly, any questions on the work of Peterborough? Peterborough is a really exciting pond to work on, and we've got lots of things we'd like to do out at Peterborough. Questions? No? Okay. I'll give you a 15-minute break, and maybe Pierre, do we want to chat?
Or if you want, you can do it at the end of your class. Is it what time do you finish?
It'll be 8:30 in the evening, and I haven't had dinner yet, Pierre.
Okay. I mean, if you have 2 minutes, we
Can
can.
we? Are you? I'm aware of this, Pierre. We've got we're in our usual situation at the end of the year because it's the end of our academic year.
Yeah.
Everybody's trying to get a lot of things finished. Just imagine you before July
Yeah.
and
It's
August.
kind of yeah.
It's chaos.
It's
Can we
chaos.
can we organize a time? Are you available? I've got our biofilm center has its annual meeting 3 days
Yeah.
next week,
Yeah.
and then we're trying to finish building Angerston. So I'm out Thursday and Friday. But the week after, could we organize a? Can I book a time with you, like this
Sure.
this time in the like we start at 9 o'clock your time in the morning? Because
Yeah.
I really would like to talk to you about what we're going to do with. I mean, I can get to Regina's paper after this, but it'd be really good to talk to you about it. Is that okay?
Okay. Sounds perfect. So the week of December the 2nd.
Yeah, let's do that.
Okay. Okay. Do you
Uh,
want me
I'll
to send you a couple
yeah
proposition?
yeah. Send me an invite by Teams,
Okay.
like 9 o'clock in the morning,
Like
and
the third. Is it good for you? The 3rd of December?
let me have a look. Let me just go in and see what I might be doing on. It's really crazy here at present. What will happen is it will become less crazy as people get nearer to the holiday time, and
Yeah.
they'll just say, "Nah, can't be bothered. It's all too hard." Um, yeah, let's do the third. Send me an invite for the third,
Sounds good. I'll send you an invite.
okay? And I'm aware that I said I'd try and do something on the paper, but I would like to do something before we finish,
Yeah.
for Christmas.
Yeah,
And
yeah. I mean, it's more how we organize ourselves for each other between each other to like to share the work because right now I have less classes, so that's why I'm working on it since like this week back on it because
right.
I work full classes and since like my classes are quite slowing down, I have much more time. So
Yeah, and that's what I'd like to do. I have more time as well after next week.
all right,
I'll have more
perfect.
time,
Sounds
and it
good.
would be good. It'd be good if you've got anything you want to send to me before that meeting on the third.
Mm-hmm.
Then that would be good. If you've got anything you've got text you've worked on or whatever,
Yeah.
send me the current version and let's see where we are.
Yeah. Do you have like your version? Because I remember when you went in France in June, you were working on a draft. On my part, I was writing the methodology. Uh, do you want me to maybe to combine the two and to
Oh yeah,
work on
yeah.
it?
That would be great. If that's what I wanted to talk about. That's one of the things I wanted to talk to you about was that revised text that you've done with the methodology that you sent
Yeah.
to Regina
Yeah.
and Asta. If you could insert that where you think it needs to go in the text.
Yeah. So could you
Uh,
send me your last version because I don't think I have it. This way
oh, okay. Oh,
I can combine it. All right. Perfect.
yeah,
Perfect,
I'll
Laurent.
send you that version. I mean, if I do find time, I mean, as I said to you before, one of the things we were talking about was that business of the validation and how she did the velocity
Yeah.
measurements and how
Yeah.
she did the comparison. I think we need to talk about that. But I think I said to you, I've pulled some of the figures out of her
Mm-hmm.
thesis that I thought uh, we need to discuss about which ones needs to go in there, and that would be good to do on the third.
Yeah. Yeah. Absolutely. So yeah, if you have like the last version right now, I can work on it. This way, on the third, we can discuss a bit further the
Yeah.
way, and this way I would have time to work on this before the third, it would be perfect.
The other thing I want to I'm hoping to be able to set up here, and you can advise me,
Oh, I don't
is
know about that,
yeah, you can, yeah,
but
you
shoot.
can. We wanted to, we talked when you were over, we talked about these linkage grants with industry, and we talked
Yeah.
about Veolia and Suez and Total.
Hmm.
Well, we're I've I've talked to SA Water, the ones who are funding the ponds at
Yeah, yeah.
Angaston,
Hmm.
and they're interested, but they always play it where we need a business case. What's the benefit to them and what's the business case? But we're going to have what I was interested in is when would we when would we be able to meet before the Christmas break with you
Sure.
guys, like
Yeah, with
Pierre,
Jeremy,
Jeremy, Guillaume, Mariana,
Guillaume.
where we could get a Teams meeting. We've got some ideas. We're going to meet probably that week of the third. We're talking about the 3rd of December, just to get. We're going to meet with right. You met Ryan Cheng, who's the
Yeah,
guy who's our link into SA Water. We're going to meet with him to say, okay, what do you think your utility is interested in to do, particularly out at Angaston? What do you want to do? What do you think would be beneficial to work on?
yeah,
And have that, and then combine it with what would you guys want to do in that linkage, not the coach hotels, but this postdoc with sequencing batch reactors, maybe modeling sequencing batch reactors,
mm-hmm.
etc. And try and get something where we've got a framework where we've sort of got some idea, we know what we're going to do, because we have to put it in March, and by March, and our university is like, January is like your August. Everybody disappears.
Mm-hmm. Yeah,
And we'll be really rushing it. It'd be good if we had some sort of thoughts about what do you guys want to do in this space, and what can we do, and how does it fit with either Suez, or if Jeremy can find time to talk with them, or because we talked about both of us meeting with Suez and Veolia and maybe Total and talking about Peterborough and algal products coming out of Peterborough, that sort of thing. We need to have a conversation, I think, before the end of the year.
okay. So I talked to Jeremy, Mariana, and Guillaume about this. We tried to
Yep.
find a discussion before, yeah, before the end of the year with just
Yep.
you or SA Water, just to you.
No, it'll be we'd have Ryan in the meeting as well, I think, because it's always good to bring them along and they can hear the discussion.
Okay, okay, okay. So it's a meeting with you and Ryan, and yeah, with the point is to discuss all the possibilities for industrial application on our side, and
Yep.
with the industrial partners we could have also, Suez, Total, to move on,
Yep.
knowing that we have to put in before March
Yep.
the application. Is that right? Did I get the thing
That's
right?
right.
Okay,
Yep.
okay, sounds good.
Exactly. So I'd just like to, kick the ball off, get it going so we know what we're talking about, because then we can, we need to get we need to get SA Water, because SA Water on board on
Mm-hmm,
side, because it's their facility we're working on, so they need to be seeing advantage to carrying on the work.
mm-hmm. Okay,
Is that
yeah,
okay?
sounds
So
good.
if you
So
could
yeah, I talked to Jeremy, Marina, and Guillaume, and we try to find the
find a
time.
time.
Yeah, before at end of the year is going to come quickly, so we need to do it now to find the right time to be
Yeah.
us us four, five, six, actually six people together
Yeah,
before
I
the
know,
end.
and that's where the difficulty is. And
Yeah,
we'd be as accommodating as we can here to get the time. We'd make the time,
yeah,
but just not next week.
yeah, yeah. Yeah, no, no, I got this part. I got this part. All right, Rod. Thank you very much.
Okay.
I will have to go because I have a meeting with Thibault, my PhD candidate. But
Yeah.
we'll keep in touch.
Yeah, and thanks for attending. I just thought it was interesting just to get you to comment about the CFD. I don't know if that was good, but never mind.
I mean, always a what. And I was like, when I was reading Regina's thesis yesterday, being on site, you see things differently after that.
Yep, exactly.
Yeah, you understand
You
things like a
understand?
bit more, like it's yeah, it wasn't all for nothing. I mean, it was really nice to like you understand things that it would be maybe not like as easy to understand just by pictures and reports.
Yeah.
But yeah,
I think it clarifies just the difficulty of doing those sort of measurements and the accuracy you can have, you
yeah,
know?
yeah. When you
Okay,
are a
that,
modeling guy just behind your computer, everything is easy.
yeah, that's right. But when you're out there with the heat and the flies, it's gets a bit irritating, you
Yeah,
know?
absolutely. And how the constraint, I mean, as you talked earlier with this sort of oxygen and everything, it's quite interesting. All right, thank you, Howard. Thank you so much. We keep in
Yeah,
touch.
nice talking to you, Pierre. Take care. Cheers.
Thank you. Take care. Cheers. Cheers.